You flip a switch, and the light turns on. Simple, right? Not quite. Behind that moment is one of the most complex machines in the modern world, the electric grid. It powers our homes, our cities, our factories, even the phone or computer you're using right now. And today on Brain Snacks, we're breaking down how the grid works, where it came from, and what's being done to modernize it for the future. Let's start with the basics. The electric grid is a massive system that does three things. It generates electricity, it moves electricity across long distances, and it delivers it to your house or business. We call those stages generation, transmission, and distribution. First, how is electricity actually made? Electricity is generated by converting other forms of energy, like heat, sunlight, wind, or water, into electrical energy. In most cases, it starts with a turbine. In a gas or coal plant, fuel is burned to create heat, which boils water into steam, which spins a turbine. In a nuclear plant, atoms are split in a process called fission, releasing heat to do the same thing: make steam, spin a turbine, generate power. Hydropower uses falling water to directly spin turbines. Wind turbines spin with the breeze. Solar panels are different. They don't use turbines. Instead, they use semiconductors to convert sunlight directly into electricity. All these sources ultimately feed power into a generator, which uses magnets and copper coils to convert mechanical energy into an electric current. But when electricity first leaves a power plant, it's not ready to travel far. At low voltage, too much energy would be lost along the way. That's where step-up transformers come in. Think of a transformer like a pressure booster. It doesn't create more electricity. It just squeezes it into a tighter, more powerful form. More technically, it raises the voltage, kind of like increasing water pressure, so it can travel through a long hose without slowing down. So, right after electricity is generated, a transformer boosts the voltage, sometimes up to hundreds of thousands of volts, and sends it out over high-voltage transmission lines. Now it's ready for transmission. Electricity travels along those massive metal towers you see across open landscapes. These high-voltage lines carry power across entire states, from remote power plants to big cities and suburbs. When the electricity gets closer to where it's needed, step-down transformers reduce the voltage to safer levels. Then comes the distribution stage. This is the part of the grid that delivers electricity directly to homes, schools, factories, and stores. Local utilities, often municipal providers or regional electric companies, manage these systems. They maintain the poles, wires, meters, and substations that make up your neighborhood grid. They're also the ones you call during an outage, and the name you usually see on your electric bill. Distribution networks operate at much lower voltage than transmission lines, and they're highly localized. In some areas, they're run by public entities. In others, by investor-owned utilities. And increasingly, they're becoming part of the innovation story. With smart meters, rooftop solar integration, and battery storage at the edge of the grid. Now let's rewind a bit to where it all began. In the 1880s, Thomas Edison built the first commercial power plant in New York. It used direct current, or DC power, which worked well up close but couldn't travel far. Then came Nikola Tesla and George Westinghouse, who championed alternating current, AC power, which could be transmitted over much longer distances. AC won the quote-unquote war of currents, and by the early 20th century, utilities were stringing wires across cities, then states, and eventually across the country. Today, the U.S. has three major grid regions: the Western Interconnection, the Texas Grid, and the Eastern Interconnection, which is by far the largest. The Eastern Interconnection covers everything east of the Rockies, about 2/3 of the U.S. population. It spans from Florida to Maine and stretches west to the Dakotas. While it operates as one large system, it's made up of many regional operators like PJM, MISO, NISO, and others, who coordinate power across state lines. Together, these grid regions include over 600,000 miles of transmission lines and connect more than 11,000 power plants. But there's another important piece of the puzzle: who controls the electricity and how it's priced. That brings us to regulated versus deregulated markets. In a regulated market, utilities are vertically integrated. They generate, transmit, and deliver electricity to your home. Prices are set by state regulators, and you don't choose your electricity provider. In a deregulated market, generation and delivery are split. You might still get electricity through your local utilities wires, but you can choose who supplies the power, whether it's a traditional plant or a green energy provider. The idea is that competition leads to lower prices and more innovation, and in many ways it has. Most of the cutting-edge innovation in energy today, like real-time pricing, peer-to-peer energy trading, and customer-side technologies, is happening in deregulated markets, thanks to competitive pressure. But deregulation isn't a silver bullet. Prices can swing more, and long-term investment may be less coordinated. Only about half the US is deregulated today, and it varies widely by state. Regardless of structure, there's one growing challenge everyone's facing. Demand is rising, fast. The US grid was designed for a world of light bulbs, dishwashers, and desktop computers. But now it's being asked to power millions of electric vehicles, new data centers processing AI and cloud computing, heat pumps replacing natural gas, battery storage, industrial electrification, and more. By some estimates, US electricity demand could rise by 15 to 30% over the next decade, or even more, depending on how fast technology adoption moves. That puts enormous pressure on both the generation and the wires that carry it. So how do we keep up? Enter the smart grid. Here are just a few innovations changing the game. First, grid-scale batteries. These store excess solar or wind power during the day and release it at night. That helps smooth out the ups and downs of renewable energy. Second, advanced sensors. These give operators real-time data on voltage, frequency, and weather, so they can spot problems early and prevent outages. Third, demand response programs. These let smart appliances automatically reduce usage during peak hours. Your AC might dial back slightly without you even noticing, but across thousands of homes, it makes a huge difference. Fourth, vehicle-to-grid charging. Electric vehicles don't just pull power, they can also give it back. In the future, your car could help stabilize the grid when it's parked. Fifth, microgrids. These are small, self-contained power systems that can operate independently. If the main grid goes down, a microgrid can keep a hospital, school, or neighborhood running. And lastly, AI and predictive analytics. These tools help forecast demand, weather, and equipment failures, allowing the grid to adjust before problems even start. And it's not just about the tech, it's about the design. New transmission lines are being planned to connect windy areas to urban centers. Solar farms are being paired with batteries, and some utilities are burying power lines to reduce wildfire risk. But this all raises big questions. Who pays for it? How do we make sure upgrades reach everyone, not just wealthy neighborhoods? Do we keep centralizing the grid, or build more local independent systems? And how do we protect it from cyber attacks, extreme weather, and all the new risks of the 21st century? The electric grid was one of the greatest inventions of the last century, but now it has to be reinvented to power everything from heat pumps to AI servers to driverless cars. So the next time you flip a switch, remember, behind that simple moment is a vast, invisible network that's being reimagined in real time. That's all for this episode. Thanks for tuning into Brain Snacks. Subscribe for more big ideas explained simply.